Hello everyone, welcome to today's SF seminar, episode 14. Today we have a new speaker with us, Yihan Geng. She's a third-year undergrad from Peking University, and she's also the co-first author of this paper. Her research interest lies at the intersection of foundation models and the reasoning abilities of large language models, a topic that's become increasingly relevant in both theory and practice. Today, she'll be sharing her recent work titled Theoretical Benefits and Limitation of Diffusion Language Model. And I'll hand it over to you, and please go ahead.
Okay, thanks for the introduction. And is it good? Okay, so hello everyone. I'm glad to be here to give a talk on our recent work, and please feel free to interrupt me if you have any questions. And yeah, so the title of this talk is Theoretical Benefit and Limitation of Diffusion Language Models. And basically what we did is that we analyzed the performance of one specific type of diffusion language models called the mask diffusion models. And here is an overview. Here's an overview of the talk. So first, I'll begin by introducing the mechanisms behind mask diffusion models, or MDMs, as we call it, mainly focusing on how they work and the key features of their design. And then we'll step into the main topic of the talk, which is the efficiency-accuracy trade-off in MDMs under different metrics. I'll walk through the main theorems and discuss their implications. And following that, I'll present some experimental results that can support our analysis. And finally, I'll briefly discuss the potential directions for future research. So let's begin. So we all know that current large language models like the transformer-based ones or SSM-based ones, they just mostly follow the autoregressive paradigm to perform next token prediction iteratively, and they have shown incredible abilities. However, despite these achievements, this sequential sampling of tokens may face challenges such as low efficiencies and difficulties to control, and especially when facing long sequences or special tasks. To address these inefficiencies of autoregressive models during inference, several strategies have been proposed, including reducing the computational cost of generating each token or decreasing the total number of execution steps required. And the discrete diffusion models, or also known as diffusion language models, which we'll be focusing on today, take the second strategy. Instead of generating tokens one at a time, they're designed to integrate the parallelism of diffusion models into text generation by generating multiple tokens simultaneously at each step. So over the past few years, discrete diffusion models have gained increasing attention for their innovative approach and promising results. So here, as I show on the slide, these are some performances of some recent diffusion language models. Like here's the LADA, and these are Dream 7B. So they have achieved performance comparable to that of autoregressive models across a wide range of tasks, and they have highlighted the strengths and potential of this new paradigm. So here, I'll briefly introduce the mechanisms of it. And the generation process, or also known as the reverse process of these models, they usually begins with an initial sequence, and then it iteratively modifies tokens in the sequence to form the final sequence, as is shown in the GIF below. And based on the initialization strategy, discrete diffusion models can be divided into two categories. The first category begins with the initial sequence of a special kind of token called the mask tokens, and this type of diffusion models is usually referred to as mask diffusion models. Some classical MDMs are SEDD absorbed and RADD. And the second category begins with a sequence of randomly chosen tokens that are either uniformly sampled or sampled by customized distributions. And within these two categories, MDMs display superior performance and scalability over the other and have become the common choice. And in addition, the scaled up models such as LADA and Dream before, they're generally based on MDMs. So we primarily focus on mask diffusion models in our work. So here's an overview of the main mechanisms of mask diffusion models. It is to iteratively replace mask tokens with tokens predicted by the model, and each token can only be replaced once. And in other words, for the standard strategy, non-masked tokens will remain exactly the same after it is generated. So next, I'll introduce some key concepts of MDMs, and here is a brief summary. Given an ordinary sequence, its tokens can be masked during the so-called forward diffusion process. By converting this forward process, you have a reverse denoising process that reconstructs sequences from entirely masked sequences, which is exactly the generation process of the model. One thing I have to note is that, like I previously mentioned, the reverse process allows multiple tokens to be generated at the same time, and these tokens are generated independently from each other. As both a preview of our topic and a reflection on the features of MDMs, I'll present our hypothesis here first before formally moving into our analysis after introducing the framework of MDMs. So the parallel token generation, or called parallel sampling, is exactly the key to the design. We would easily guess that it can speed up inference compared to autoregressive models, but one question remains, is that will this hurt generation quality? And this is actually a natural hypothesis, and as an insight, let's take a direct look at the following example. So without any further context, these two sentences presented on the slide are both fluent and reasonable, and they share the same tokens except for the ones in the blue boxes. So imagine that we have to generate this sentence, and if we're generating tokens one by one, and assume that the model is well trained, then a token in the second blue box will know no matter what it is. It's I suppose that it must be consistent with the first one, right? But however, consider generating the sequence with mask diffusion models. As I'll explain later, the traditional sampling strategy of MDMs modifies mask tokens in a random order, which means there exists a probability that all tokens are generated except for these two tokens. Given that the two sentences above are all reasonable solutions, and that these two tokens may be generated simultaneously and independently, it is likely to be a twist and generate something like he bought 2 dozens for $5 or 1 dozen for $10, which is just incorrect. And this inconsistency just comes from parallel sampling. So you can acknowledge that there is some sort of trade-off between the efficiency and generation quality of MDMs, but the more critical question we seek to answer is, to what extent does parallel sampling impact performance, and is that acceptable given the efficiency gains it offers? So in the following sections, we aim to answer the question, do MDMs achieve superior efficiency when the generated content meets an acceptable quality standard? But before going deeper, we have to first take a closer look at the theoretical framework of mask diffusion models. As I mentioned earlier, given an input sequence, the forward diffusion process gradually replaces its non-masked tokens with the special masked token denoted as M. And this process is controlled by a non-decreasing function alpha t, referred to as the masking schedule, where t represents time ranging from 0 to 1. And here, to be more precise, let xt denote the sequence at time t that consists of a mixture of original tokens and masked tokens. And the initial sequence is denoted as x0 and the fully masked one as x1. So assume that Q represents the true data distribution over sequences, and the distribution of xt can be factorized across positions, since each token in xt is independently sampled from either M or the original token, with probability determined by the masking schedule as here, like as in this equation. And the masking schedule of t is designed to satisfy that x1 is fully masked and x0 is fully unmasked. And building on this forward diffusion process, you can define the true reverse process here that starts from a partially masked sequence at time t and aims to reconstruct the original sequence by reversing the dynamics of the forward process. And the equation here describes the conditional distribution of xs given xt, where time s is smaller than t, sorry. And this expression is computed by marginalizing over x0, and the probability of each token is derived from the forward process. Although we won't go into the full derivation here, it is important to note that the distribution of xs is approximated as a product over independent token probabilities for simplicity, as I marked in red. And this assumption enables parallel sampling, but it also introduces a potential trade-off in accuracy. So in practical settings, this reverse process is often implemented by first generating a sequence at time t and then applying the forward masking process to reconstruct the intermediate state xs. So if we accept the nature of this reverse dynamics as shown on the slide, then in order to generate sequences under a given masking schedule, the key value that we need to approximate here is also marked in red. So we want to use neural networks to approximate this probability so that we can just reconstruct the whole reverse denoising process. And this slide presents a more formal expression of the final idea from the previous slide. So in short, we use a neural network to predict the probability distribution over tokens for each masked position at time 0. And these predictions define the model distribution of x0 denoted by p theta here. And this is then used to perform parallel sampling. So by using the fact that alpha 0 equals to 1, and we can derive this formulation, where's my mouse? Yeah. So you can derive this formulation directly from the forward and reverse dynamics we just discussed. And I want to highlight again that based on this formulation, the model predicts each token independently at each steps. That is, it ignores interdependencies between tokens within the sequence, which is a simplification that makes parallel decoding feasible, but potentially at a cost of output coherence or fluency. So this brings us back to our initial hypothesis that there may exist an inherent trade-off between efficiency and generation quality in masked diffusion models. And now we'll step into our main analysis. So, but given the hypothesis we aim to examine, a fundamental question emerges, that is, how do we evaluate the efficiency and the generation quality of a model? Well, at first glance, it may seem straightforward because a variety of evaluation metrics already exist. However, prior works have shown that model performance can vary depending on the choice of metrics, and our previous counterexample captures a sense of overall consistency, and in contrast to perplexity, which primarily captures token level performance. So it's quite important to choose the suitable evaluation metrics. First, let's just revisit the main perspectives from which we evaluate the performance of language models. So these perspectives are relevant to both the purpose of the evaluation and the intended downstream application. So for general text generation tasks, the fluency of text is a common consideration. Like it's very natural, and um but for reasoning or other structured tasks, the correctness of the sequence is considered to evaluate whether the generated text match certain rules or produce the correct results. Efficiency remains a critical concern across all settings. And this efficiency can be examined directly by measuring the number of execution steps or real-time computational costs. So we only have to focus on the first two here. So for fluency and correctness, common evaluation metrics include perplexity and accuracy respectively. So as you all know, perplexity quantifies the uncertainty of a model in predicting the next token in a sequence, with lower perplexity indicating better fluency. It just serves as the standard measure for assessing the quality of text generation, and accuracy here mainly referred to the benchmark accuracy of reasoning tasks such as math or coding, which calculates the correctness of generated answer. So here we outline some guiding principles for choosing our evaluation metrics. Based on our earlier assumption that parallel sampling may hurt the sequence level consistency of text due to the disregarded interdependencies, we conjecture that token level and sequence level evaluations may lead to different conclusions. So because this inconsistency is more of an issue of correctness than that of fluency. So we want to measure the performance from both token level and sequence level. And building on these considerations, we propose two evaluation metrics, which are, wait. Wait, can I, oh, sorry. Yeah. They are token error rate and sequence error rate. So first, token error rate, or TER, it is directly defined by generative perplexity. And if we denote the ground truth distribution as Q and the evaluated model as P, then we have the exact like this expression for TER. And here the exponent is the cross entropy of P and Q, and the logarithm here takes base 2 as its common. And just like perplexity, we know that models with lower TER value indicate a model that is better at generating fluent and coherent text. And on the other hand, the sequence error rate, or SER, evaluates the correctness of the entire sequence. It quantifies the probability of the model to generate sequences that fall outside the support set of the ground truth distribution Q. In other words, it reflects the probability of the model to generate an invalid sequence. So formally, if the ground truth Q has a vocabulary V and the support set basically consists of all valid sequences permitted on the Q, and SER just measures how likely the model will generate sequences that are not in this specific set. Yeah, it may be a bit complicated, but the idea is kind of trivial, I suppose. So to summarize, lower TR means better token level accuracy and higher fluency. And in contrast, SCR evaluates the correctness on a sequence level rather than individual tokens, making it stricter than TR. And the accuracy used for many reasoning tasks that I mentioned earlier is actually a special case of SCR, because in these tasks, correctness is typically judged based on the final answers. So any sequences with the correct answers constitutes part of the support set in the definition of the corresponding SCR evaluation. And from this perspective, we claim that accuracy is actually a weaker metric than SCR because it just neglects many structural or logical inconsistencies that can be important in practical applications. So SCR is particularly well suited for tasks that demand logical consistency, reasoning, or structural integrity. And since we are mainly concerned with how parallel sampling affects the efficiency and generation quality of MDMs, we only focus on the performance and inference cost of a well-trained MDM, and whether achieving such well-trained models is feasible in practice is beyond the scope of our work. So here's our assumption. We just simply assume that the MDMs are able to learn the data distribution with small errors. And formally, given a target language and a masking schedule, we hope that there exists a small epsilon such that the KL divergence between the data distribution and the model is always smaller than epsilon. And when epsilon approximates to 0, actually the loss of the model also approximates to 0. So now that we've established our assumption, let's talk about the main theorems of our work. For token error rates, there exists an upper bound of TER for n-gram languages. And this theorem on the slide actually tells the following fact that given any n-gram language Q and a well-trained model P for any epsilon, and if the sequence length L is large enough, then there exists a masking schedule that guarantees a relatively low TR of P with a moderate number of sampling steps independent of DL. And to be more precise, the logarithm of token error rate of P will stay close to that of the true model Q, plus a small error term from imperfect learning and a factor that depends logarithmically, like on the vocabulary size. And this term can be very small. So I will not derive the theorem here because it's a bit complicated. But if you're interested, we have the whole proof of the theorem as well as an outline of it in the appendix of our paper, of course. The masking schedule we proposed in this theorem is actually nothing special because basically it was like having a higher chance to sample more tokens at the first step, and other steps share the same probability. Well, which is actually kind of common practice in mass diffusion models. And one thing that you might ask here is why we use n-gram languages. Well, first it's for simplicity, and also n-gram languages, as you all know, they can approximate real text. And here it's important to note that we can generate incredibly long sequences while still maintaining a low TR, which is the main idea of this theorem. So at a higher level, if an MDM learns the data distribution well enough, then it can generate long sequences efficiently with a high fluency. And here are some comments on this theorem. First, note that for any model P trained on the true model Q, the optimal TR is simply TR of Q, so it is sufficient to focus on the upper bounds. And now here's the key advantage of MDMs. Unlike autoregressive models, the number of sampling steps required by MDMs does not grow with the sequence length. And this is a huge efficiency gain, especially for generating long sequences. So from this perspective, we can conclude that MDMs show strong potential for text generation, or at least when we are evaluating with token error rate or equivalently perplexity. And but however, recall our earlier analysis on parallel sampling that it may lead to irreducible errors in the sequence. We start to wonder whether this conclusion still holds for sequence error rate. But regarding SCR, we first show that with sufficient sampling steps, the sequence error rate of a well-trained mass diffusion model can be very low. In this setting, we consider any hidden Markov model key as the target. This theorem on the slide tells us that as long as the MDMP is well trained with a sufficiently small learning error, given enough sampling steps, we can make the sequence error rate below any desired threshold delta. Intuitively, this is because that when the number of sampling steps is large enough, the reverse process of MDMs is similar to generating tokens one by one. And thus, if the model has learned the correct data distribution, this process becomes highly reliable at producing correct sequences. So therefore, MDMs do have the ability to generate correct sequences. However, if we consider the efficiency, the seemingly good performance might not be the case. So in this theorem, we construct a specific HMM with just mild assumptions to serve as an example, I would say. The goal here is to show that even for a well-trained MDM and any fixed masking schedule, there can be cases where the sequence error rate remains unexpectedly high, and even when the number of sampling steps scales linearly with the sequence length. And here the constants C and parameters like 16, they only serve to highlight the key idea more clearly, and replacing them with similar values wouldn't change the core insight here. So when we combine this result with the earlier and also more optimistic findings on TER, we get a more complete picture of MDMs that while MDMs are theoretically capable of generating correct sequences, the computational cost required to achieve a low SCR can be substantial and potentially much higher than what TR alone might suggest. In other words, strong TR doesn't necessarily guarantee low SCR at a reasonable cost. And this is the HMM that we used in the theorem, and the main idea is actually quite simple. So we construct a sequence by dividing into small independent segments of 5. And within each segment, certain pairs of tokens, which are shown here as blue lines, like here, they're constrained to have the same value, either 0 or 1. And each token in a segment uses a 4-digit binary number to record the values of 4 specific token pairs represented by 4 blue lines connecting to it. So like if this is a token, then it has these 4 pairs. So for instance, if those 4 values of the lines are 0, 1, 1, and 0, let's say, then the token would correspond to the binary string 0, 1, 1, 0. So in this setup, each token is a 4-bit summary of 4 other tokens, and the key constraint is that the values must be consistent across the pairings. And the tricky part lies in the tightly coupled structure, where sampling multiple tokens in a parallel and within the same segment can easily result in inconsistencies, such as one side of the pair says 0 and the other says 1, and these inconsistencies lead to sequence level errors. And the reason we construct this example is that although we acknowledge the importance of sequence level consistency and accuracy, it is actually somehow hard to quantify. So this example would be a vivid demonstration of how parallel sampling may influence consistency. And here are some comments on SCR. So yeah, from the second theorem, we know that in order to ensure the sequence level accuracy of generated text, the number of sampling steps have to scale at least linearly with the sequence length L, and this is much stricter than TER. Meanwhile, since the average computational cost of one inference step in autoregressive models may be lower than that of one reverse step in MDMs, we can conclude that regarding SCR, MDMs are less efficient compared to autoregressive models. And although there are efficient sampling strategies proposed in prior works, such as the DDPM cache or something, which can reduce the computational cost, the conclusion before still remains true. So to conclude, the theoretical results before show that MDMs can generate low TER sentences and offer efficiency gains over autoregressive models, but might fall behind when evaluated under SCR. And this may seem a bit contradictory, so one would naturally ask that do TER and SCR conflict? Well, exactly, not exactly, but they can paint very different pictures of how well a model is doing. And this brings us to a broader and sometimes underrated point in machine learning, that the metrics we choose actually shape the story you end up telling, even with the same model and the same outputs. Like, for example, some have argued that the emergence phenomenon may stem from using the non-smooth evaluation metrics. Just think about how perplexity is everywhere today, but it doesn't always align with actual model performance in more complex tasks, just as several prior works have shown. And this is the same with SER and TER. Um, you might get great TR scores, while it does not necessarily mean the output is globally correct. Therefore, there's no such a gold metrics for all tasks. And in this specific case of MDMs, you want to highlight the importance of assessing the model at a sequence level. So here is a brief summary of the takeaways from our theorem. So our main conclusion is that MDRMs are great at generating fluent sequences, but suffer from great efficiency, accuracy trade-off respect to SCR. And compared to autoregressive models, MDMs are more optimized for fluency than precision, so they can work really well for general text generation, but they might struggle more with tasks that require tight logical consistency or step-by-step reasoning, I guess. But just to be clear, so all of these applies to traditional mass diffusion models. And there are certainly promising directions to address this issue, which will be discussed later in the future directions section. But for now, we'll head to the experiments. So to validate our theoretical findings, we conducted a series of experiments. We began by training MDMs and autoregressive models on our synthetic languages, specifically Ngram and HMM-based ones, because that's how our theorem suggests. And these controlled settings allow for precise definition and evaluation of TER and SER. Furthermore, we evaluated open source diffusion language models on both text generation and math reasoning tasks. And these preliminary experiments aim to demonstrate how our insights align with real world performances. So, for synthetic experiments, the N-gram and HMM languages are generated with randomly chosen parameters such as transition matrices and etc. While TR can be evaluated by perplexity, SCR requires that there exist sequences falling outside the support set of the languages. So to this end, we introduced a thresholding mechanism that prunes the low probability path, thus ensuring that there exist such incorrect sequences. And for training, we employ the widely used transformer-based architectures as the backbone model. And both the MDMs and the autoregressive models were trained for 20 epochs under comparable settings. So this is the first of our experiments. This figure shows the TR and SCR of generated samples of length 512 across different formal languages with the number of sampling steps varying. And here TR is measured by generative perplexity because they're the same, and SCR are evaluated by the models, like we have some incorrect ones, so we can evaluate it. And the x-axis in the figure represents the number of sampling steps ranging from 8 to 2048, and the y-axis measure the generative perplexity and sequence error rate respectively. So the performance of the autoregressive model is marked as a reference point here at the end for comparison. And the relative speed up is noted at the top of the figure here. Yeah, so as the figure shows, the TR of MDMs converges to that of autoregressive models while maintaining a speed up. But for SER, even when the number of sampling steps reaches like here 2000, there still remains a gap between MDMs and autoregressive models, and the improvement here is comparatively slower than TER. And this is consistent with our theoretical analysis that MDMs are highly efficient at generating fluent sequences as reflected in the low TER, but they can struggle with global sequence correctness. And to better understand how the token error rate of MDM changes, we also conducted experiments to evaluate their performances across different numbers of inference steps and sequence lengths. So for consistency with the previous theorem, we tested on 2-gram, 3-gram, and 4-gram models. So the percentages here in the table represent the relative increase of TER, where a lower value indicates better alignment with the ground truth. And our results reveal a clear trend that for any fixed sequence length, increasing the number of inference steps consistently reduces the error. And more importantly, as the sequence length increases, the error does not scale significantly, but rather stays at a similar level. And these observations align with our theoretical insights that the number of sampling steps required by MDMs does not necessarily need to grow with sequence length. And since we've observed that in our settings, when MDMs the MDMs are running with 512 sampling steps, their performance gap with autoregressive models becomes negligible. So building on this fact, we measured the inference time per sequence of both MDMs with 512 steps and autoregressive models across a range of sequence lengths here. So yeah, so these results here shown they so the exact language doesn't matter here. So because you only care about the efficiency, and as is in the table, MDMs begin to demonstrate efficiency gains over autoregressive models once the sequence length exceeds 2,000 tokens, which again showcases its ability in generate fluent text. So, and now we turn to experiments on existing large language models. So for the text generation tasks, we compared a mass diffusion model trained on open web text. Yeah, if I remember it correctly, called the NDLM OWT with GPT-2 medium, which serves as a baseline because they have similar sizes. We compare them. We compute their average generative perplexity over 2,000 samples and each of 1,024 tokens. Yeah. So in this figure, the x-axis, y-axis, and the numbers here are similar to the previous ones. So as is shown in the results, the MDM matches the generative perplexity of GPT-2 medium with only 32 steps, where there's an over 2 times speed up, and the perplexity continues to decline and converge as the number of sampling steps increases. So this highlights that MDMs can generate text efficiently while ensuring a high fluency. Which illustrates the potential of MDMs for basic text generation tasks at a larger scale. And this is for mathematical reasoning, and we chose GSM 8K. Although the formal definition of SCR does not directly apply here, real-world reasoning tasks such as solving math problems usually demand a high level of global sequence consistency. So we believe that this task is also a practical approximation of SCR performance. So we evaluate the performance of an MDM fine-tuned on math with well, actually we didn't compare it with the autoregressive models because there are many co-founders, and it is so only shown here for reference. And the main idea of this figure is that although the average length of the generated answers is only about 30, but as you can see, when it hasn't reached 32, the general accuracy is still below its maximal performance. Although it then reached higher scores here, but we assume this is because the model we tested is not strong enough, but the decline here just shows that the model it just shows that insufficient sampling may be a severe issue to tasks requiring strong logical coherence. So in summary, our findings highlight the trade-off of traditional mass diffusion models between efficiency and accuracy, depending on the evaluation metrics. And here are some directions for future research. So first, we want to offer some insights on potential pathways to mitigate the SCR limitation that we showed. Our theory assumes that our theory uses the standard sampling strategies, but some novel sampling methods may offer improvements, And additionally, the diffusion models we examine in our study rely on conventional masked language modeling, where once a token is generated, it remains fixed and cannot be revised in later steps. Well, we think that this prevents the correction of early errors and potentially leading to higher SDR. And several recent error correction mechanisms, such as the remasking one, have been proposed to address this issue. And actually, I would say that the sampling masses and like remasking mechanisms are to some extent equivalent, because like we just generate the sequence at time zero and we masked it at time s. So I would say they're just two sides of one problem. And beyond this, other discrete diffusion models beyond the mask setting, such as the SEDD uniform and DFM, may present potential solutions. And looking ahead, there is a broader theoretical and empirical question, which is, what is the efficiency accuracy trade off of a broader family of diffusion based language models in real world settings? And extending our theorems to address this question is also an important path for future research. And lastly, we assume the availability of a well trained diffusion model. Whether such models can be effectively trained on in practice, it remains a critical open question. And we believe that a deeper understanding of their approximation error regarding different numbers of parameters and also generation length is crucial to fully characterizing the capabilities and limitations of diffusion-based language models. So yeah, um, I think that's all. And do you have any questions?
I had a quick question.
Yeah,
Thanks for the presentation. It was great. I guess one thing you touched on briefly was that you have a good speed at decoding. I had some questions about if you have any insight into speed of training for these kinds of models versus autoregressive.
well, actually, I think that the people propose this kind of model is um based on the idea that multiple tokens can be generated at the same time, so it speeds up inference. But for training, I'm not sure whether it is really quicker than autoregressive models. Well, I suppose it's I guess it is not, but I'm not really sure about it. So yeah.
No problem. Thank you. I had one other
Thank you.
question about
Yeah,
your final slide. Um,
yeah,
using the ways to mitigate the errors. You had talked about remasking strategies or
yeah.
discrete models. Have you guys done any experimentation with like using a discrete diffusion after the original masking diffusion, or have you tried doing any remasking strategies? What seems like the most promising direction there?
Well, actually, I think there are several sampling methods and um, or equivalently remasking strategies here. I've seen ones that just also randomly chooses the positions to remask, and we think that this kind of remasking strategy is actually cannot actually mitigate this problem, because if we use the example that I gave earlier, it would also cause a high sequence error rate. But there are some sampling methods that uses like the entropy of generated tokens, I think, and just to choose the ones that you generate at this step. And um, I guess that this kind of method um, can improve the SER performance, but we haven't tested on it yet. Yeah, but I think we'll test it later. Yeah.
Well, yeah, I'd be interested to see if kind of different patterns of remasking might help, or you know, you obviously have to attend to the existing chunk that was generated and while you're regenerating, which is probably not true in the original mechanism. So maybe it requires slightly different training.
Yeah, yeah.
All right, thank you.
Thank you. Any questions? Maybe there. Yeah. Any questions?
Yeah, I'll ask some questions.
Okay.
So could you go back several slides? I think there's a slide indicating the arrow, like sampling step should be linearly scaling.
This one.
I think it's a slide like comments on SC.
Oh, yeah, yeah.
Yeah, I also noticed like for the first conclusion, the total sampling steps in MDM should be like scale linearly respect to the sequence length, and I also noticed for many recent large diffusion model, their total sampling step is also amounts to the sequence length L. Do you think this is like a kind of like indication of this theoretical conclusion?
Um, yeah, some part of it, but like when we're saying scale linearly, we would think of different sequence lengths, like but the the models here we have, they usually have a fixed length, like whether it's 2000 or 1000, and I would say that to some extent it is, but um it's not that, I'm not that sure that it really, it's really the implication, like the implication here.
Oh, I see. Thank you. I think by increasing the sampling steps in MDM, it kind of mimics some sort of like autoregressive decoding.
Yeah.
Yeah. So how do you think like I think there are some connect on the fundamental trade-off between the parallelism and the expressiveness. Uh, how do you think of it in the context of diffusion large language model?
Yeah, I think that is because of parallel sampling, as I proposed earlier. Because if you highlight on efficiency, like if you want to inference fast, then you have to use parallel sampling, and there must be multiple tokens that are sampled at the same time. But this will introduce some kind of errors. But if you want to mitigate this kind of errors, at least without any further sampling strategies or like remasking mechanisms, you have to increase your sampling steps. So that is why we think the SCR limitation is really a big issue. Yeah.
Yeah. Thank you for explanation.
I suppose I have one other question with regard to
Yeah.
what someone was just asking. If you think about the order of diffusion and you think about sampling, I guess one thing that we didn't really talk about is like a non-sampled version where there's no temperature at all and you're just choosing the most likely outcome. In that situation, maybe it's possible that the model could in fact know how to create consistency within the generated chunk, because even though you would be sampling in parallel, is it possible in that situation there, because there's no randomness, the model could learn to ensure consistency?
Yeah, it is. But like, if we wait, where was? Oh, yeah. If we think of this example, if there's no randomness, then it might mean that it can only generate one of these two sentences, which is, I think, is not what we want to see, right? Like for general language models, we wanted to generate something like it can generate this one and also this one, but you can't just force it to generate one of them.
Yeah, do you think that maybe there's some, I guess I'm generally unhappy with our idea of sampling for language models in general. And I wonder if if you think there might be some different place that we could inject that kind of choice or randomness that's not at the sampling level, but is in some other part of the model, so that it can still maintain consistency by doing definite, what I guess I'll call definite sampling at the end, but in the middle, somehow we change its mind about which kind of generation it's going to do to sidestep the
Yeah,
problem.
yeah, I think that's a good idea. But I think it also needs future research because it's like the masking mechanisms, because before you generate this sequence, you actually don't know which part of it should be definite and which part of it should be randomly sampled. And um
Sorry, actually, that gives me one more idea I could add in,
yeah,
which is that maybe the randomness could be the order rather than the sampling. And so if you, uh, instead of like probabilistic sampling, if you did definite sampling, but you change the order probabilistically, then that might allow you to achieve different generations, even with the same
yeah,
underlying model.
yeah, yeah, that's right, I think.
So maybe
Yeah.
that can give us a kind of like a more, like to me, more correct analog to sampling for autoregressive, but in this mask domain. I don't know, it's an interesting thing to explore at least.
Yeah, yeah. I think it's a good idea. Yeah.
Do you think it's a promising direction to combine autoregressive generation and diffusion model?
Um well, I've seen models that like they can first you can use these kind of discrete diffusion models to generate like autoregressive models that is definite. Like you can just control it to generate the first token and the second token and so on. So it's just like autoregressive models. But um yeah, to some oh yeah, I've also seen some work that because when we're talking about discrete diffusion models, the length is always fixed, and there've been work that like generates, I would say, 500 tokens first, and then conditional on these 500 tokens and generate the next 500 tokens and so on. And I think this is kind of a good combination because like if you're generating a text status, I would say 5,000 tokens, and if you're using like the general general masking strategy, then you may generate some token at last, like at the 5,000th place first. But if you are doing this like kind of autoregressively, then it may reduce these kind of potential errors. So I think that's kind of a good combination. Yeah. And there are also sampling methods that I mentioned earlier that uses the uncertainty of your token generated to choose which place you would use at this step. And the result is more of like you generate tokens like kind of autoregressively from the first and also from the back end. They meet at the middle. I think that's also kind of autoregressively. Yeah.
I have one other question that made me think of. It's a little vague, but do you have an intuitive sense about whether it might be possible to use attention scores on the generated text in order to decide what needs remasking? Because basically my intuition here is that attention is going to generate exactly the kind of map of things that are required to be known in advance. So like in an autoregressive setting, if we were going to choose the number of things versus the cost, like you had in your example, the total cost might attend to the count or the cost per item, and therefore you might be able to know via attention which tokens could be kind of incorrectly matching. And it might give you a hint in terms of what needs resampling, or even in terms of what order sampling might need to proceed.
I'm not sure, but wouldn't it just slow down the inference? Like
Yeah.
to great, yeah.
Yeah, maybe it undoes the entire benefit. Could you go back to
Yeah.
as the example that
Which one?
the error example? Yeah, that one.
Yeah.
Or maybe the one with the dollar amount.
Okay.
All right. Yeah. Right. So I guess what I was saying is that if after generation you could generate the attention maps for this segment on itself, then you could know that the $10 is supposed to attend to the TWO, the two spelled out. And that might, for high attention things that have self-attention within the segment, you could know that it might need to be specially generated.
Yeah. I think that's also kind of like the entropy thing, like you estimate which token should stay and which token should be masked again. But yeah, I'm not sure whether this will like hurt efficiency and make it not that quick and like to mitigate the advantage of this.
Yeah, I think the reason that it's efficient is because you can do it in, just like transformers are trainable in parallel, you can the chunk entirely in parallel to generate all of the attention maps. So it might use GPUs very efficiently to do that, even though technically it's more total flops to do it. You can do it after the entire segment is generated, and so you can do the entire thing in parallel.
Oh yeah.
So it gives you like training, like efficiency, parallelization efficiency for analysis of what might be wrong in your generated segment. And so that could give you the ability to correct those errors either via remasking or something like that, or autoregressive remasking or something like that.
Yeah, I agree. It sounds like a good point. Yeah. Do you have any further questions?
That was it for me. Thank you. It was really interesting. I learned and thought a lot about how these things might be able to cause errors and maybe even how to correct the errors.
And also thank you for questions and suggestions. Yeah.
Okay, thank you for your presentation.
Yeah, thank you. So I'll stop the screen.